Trying to figure out how to do this. Hey guys and gals, how we all doing today? You got some homework to show me? Got some homework for me? I hope, believe. Okay. Rather than wait for the next correction is done. Which anybody who is doing test corrections on your Unit 4 tests, do remember, those are due this week. They are due on Friday. Whether that is in person or whether that is via pictures and email, if you're doing test corrections, they are due this week by Friday. Right? Okay. go ahead. Let's get started here. First, let's go ahead and let's put up our answers for 5-5 here. We can take any homework questions on there, any other questions that we have, anything else we want to talk about. We can start going through. Any homework problems or anything we want to talk about? Homework problems or anything we want to talk about here today?
Number 55.
55? Luke?
We do 71.
55, 71. What else we want to talk about? 83. Anything else? Anything else? Okay, well, let's start with 55. Guys, I should forewarn you, when you come in tomorrow, the classroom's going to look a little different. They're bringing me the desk I need. So classroom's going to look a little different here for the rest of the week. Not only for you guys, but for your counterparts here as well. We're just going to have to make do with the spacing and everything. Mr. Kaufman will still figure it out. We're almost done with this unit. 5-7 ends our unit tomorrow. We're on 5-6 here today. Wednesday, we're going to be looking at our next quiz. I think Thursday, we'll be looking at our study guide. Friday, we'll probably have the quiz due, and I'll probably open up the test. And we'll see how all that kind of shakes out. We'll see if we need an extra day or so in there. If we need an extra day for review, which I'm thinking some of you all might appreciate, it might be Thursday or Friday this week. We'll open the test next week. But either way, Unit 5 will be completed. It will probably be the last thing we do before we go on spring break. We have this week and we have next week, and next week is only 4 days. And then after that, you guys are all coming back. You guys are all coming back. And for us, it'll be short. For us, it's not going to be a whole lot of new information. We might do one more unit, maybe 2. The question has come up about AP testing. So there's been a couple of different plans for AP testing. But if I had to pick, and it's hard for me to pick because Ms. Leatherwood is now out on maternity leave. So it's hard for me to get straight answers because we don't really know who's even doing testing at this moment. But if I had to guess, since you guys are coming back 4 days a week, you guys will be doing in-person paper pencil test, which means 4 hours. And probably no notes. And there will probably be a calculator inactive part and a calculator active part. Because that's how your class is supposed to be ran. I was not going to run you guys with calculator inactive and active and all that type of stuff. I felt like that would not be fair. Based upon how you all did on Unit 4, I think it's pretty clear that we've had some issues. We've had some struggles. I can only imagine what it would have been like if I was giving you 2-hour test, half of it being inactive. So we will have to work our way up to that. We will have to start doing some serious review after Easter break. But that's after Easter break. Let's worry about Unit 5 right now. Unit 5, we're going to talk number 55 and go through a couple of these problems here. So let's start with number 55. You can actually see it up there on the answer sheet, bottom left. Number 55, we have the log base 5 of our root. So we have log base 5 of our root, x squared minus 1. And what we need to do here is we need to find the derivative. We need to find the derivative here for this particular function. So, best way to go about this is probably to manipulate our log just a little bit. You can see that's what I did there with my first step. I went ahead and said, okay, let's convert this back to a fractional exponent, x squared minus 1 to the 1/2. And then I use my power rule to bring that 1/2 down. That allows me to treat it like it's just a general multiplier, which genuinely makes this problem significantly easier. It makes it a lot easier because now we can just go ahead and do the standard, well, not necessarily standard, but we can go ahead and start doing some of the logarithmic derivative rules that we talked about before. So if we look at this, if I want to, I of course can go with u substitution here for what's inside. We did talk about doing that. I'll show that. If I want to set u equal to x squared minus 1, that makes u prime 2x. Good so far, right? And then, of course, we can go ahead and set up our rules here. We'll have 1/2. Log base 5 is going to become 1 over natural log of 5 times what's inside, which would be u, which is x squared minus 1, times the derivative of u, which is 2x. The only thing here that we can simplify is we can take this 2 and this 1/2 and make this x over natural log of 5 times x squared minus 1. Questions here about this one? I think that root can definitely mess some people up. There is a hint up there in the directions, however, for these ones, that you might want to apply some logarithmic forms to this before you get too heavy into it. Questions here about this one? Concerns here about this one? You could do this one further with u substitution. You could just say u equal to x squared minus 1 to the 1/2. And then, of course, that's a chain rule for the derivative of u, the u prime, so to say. Questions here? Of course, I think it's just easier to manipulate the log than to do that. Let's move down here on my execution, so that way we can see the rest of these here. We want to look at 71 and 83. Did I skip 71? I must have. It's the second time I've done that. Okay. We'll take a look at 71. Chances are I didn't intend for you to do this one when I skipped it and forgot to cut it from the assignment. Number 71, find the equation of the tangent line. Oh, we can do this. We can do this. Let's go ahead and set this up here. We have x to the sine x. What's the point here? Pi over 2, pi over 2. Okay, so ultimately, what we want to get to is we want to get to y minus pi over 2. We need m, we need x minus pi over 2. So what we really need here is m. For us to do that, we need to get the derivative of what's up here. So, how do we do that? Break down the sign. How am I going to break down the sign, sir? Nobody's got any ideas? Allie?
So you take the derivative of it and you use the natural log, right?
Okay. Tell me what you think. Tell me what the product is.
So it would be natural log of x times x up to the sine x, and then you have to multiply by the derivative, which is the sine
So natural log x times
x up to the sine of x
to the sine x, right?
times cosine.
Times cosine x. So Allie, walk us through what you've done here. So natural log x is our standard derivative, right? It's the natural log of what our base is, yeah? And then it's times the original function, right? Times the derivative of this function, which would be cosine x, right? Okay? One way to do this, I know why I cut this problem or meant to cut this problem. The easiest way to do this is to use implicit differentiation. The easiest way to do this is with implicit differentiation. And to do this as a log base x of y equal to sine x. And then you can use your logarithmic rules from here. This would be 1 over natural log x times y times dy dx equal to cosine x. That would be the easiest way to do this, is to use our implicit differentiation. But I haven't taught you guys how to do that yet, so that's why I forgot to cut this one. That is honestly my bad. Not that Allie's going in the wrong direction. We could get there that way, but I think I might put this one on the back burner and come back to it as a warm-up problem later on this week. Who asked for 71? Good question to ask. Good question to ask. We'll come back to this one once we've talked about implicit differentiation a little bit, okay? That's my fault, guys. That's my fault. Okay. And then 83. 83, we're just doing a nice standard integral here. -1 to 2 of 2 to the x dx. Okay? So this should be a pretty standard move here. What's the integral for a standard exponential? Or how we take the integral of a standard exponential? Go ahead, Allie.
It'd be 1 over the natural log of 2 times 2.
I think times 2 to the x, isn't it?
X, yeah.
Okay. I mean, guys, it's up there on the board. Come on. Why is nobody else participating? Times 2 to the x. Move the x, Mr. Kaufman. Okay. And what are we going to do with this? Normally this be it, right? Plus c. But we're going to actually plug in some numbers here and evaluate. So between -1 and 2. So we'll plug it in 2 first. We got natural log of 2 over 4 minus. This can become 2 to the -1 over natural log of 2. Which you can go ahead and make that as 2 separate fractions if you want. So this has become 2 natural log of 2 over 1. And if you want, you can actually continue to manipulate a little bit further. The easiest thing I think to do would be combine them now. Multiply the top and bottom here by 2. That makes this 8 over 2 natural log of 2. Minus 1 over 2 natural log 2, which is going to give us 7 over 2 times the natural log of 2. Or I guess if you want, you could make that 7 over natural log 4. That would also be acceptable if you power ruled that up. Questions here? Concerns here? Okay. Note back to 71. Okay. Today we're going to do inverse trig differentiation. Inverse trig derivatives. Inverse trig derivatives. So, when we talk about inverse trig derivatives, let's talk about the inverse trig functions. Talk about the inverse trig functions, or perhaps lack thereof. So we're talking trig, right? We think about sine, cosine, tangent. We think about them and all their counterparts, correct? I've been known to do that, and the students just sit there with my crap all over their desk. Okay. So when we think about sine, cosine, tangent, secant, cosecant, cotangent, think about their graphs for a minute. Think about the two tests that we have to have. Think about the two tests that we have to have. Vertical line test and horizontal line test. Now, each of them on their own, they pass the vertical line test, correct? Each of those graphs, if you think about them, they all pass the vertical line test. So meaning each one in its own right, in its natural state, all 6 of the base trig functions are inherently functions. None of them pass the horizontal line test. Meaning that while an inverse equation is possible, an inverse function is not necessarily possible. Now, there is some ways around this. So when we look at our second slide here, none of these 6 base trig functions inherently have an inverse function. Now, we can manipulate this to make that work, though. For us to do so, we have to restrict the domain. We have to cut off the cycle. We have to do this in a way that if I were to look at the original sine, cosine, secant, tangent, whatever graph, that I would eliminate where we fail the horizontal line test. So for sine and cosine, that would mean eliminating one, or only looking at one period of the function. If we're talking about secant, cosecant, cotangent, we're only going to be looking at possibly half the period of the functions. Questions here? So let's go on to the next slide. This is sine. Let's just use this as our base here. Okay, so this is what the standard sine graph looks like. Domain negative infinite through infinite, the range negative 1 to 1. So to do this as an inverse, we're going to have to cut this down so that way the function becomes 1 to 1. So that way we pass the horizontal line test. For us to do this, that means that we cannot run this function exactly from point to point. Now, standard period is typically 0 to 2 pi, is it not? Okay, 0 to 2 pi is not going to work here. 0 to pi isn't going to work here because we're going to fail. So we're going to modify this. We're going to run from negative pi over 2 to positive pi over 2. We're going to run from negative pi over 2 to positive pi over 2. That allows me to get every y value without having a double over. I can't start going back down, and I can't start going back up. So I have to go from the minimum to the immediate next maximum. This would also work if we went from pi over 2 to, say, 3 pi over 2. It is the distance, the overall distance of 1/2 the period. The period is typically 2 pi. I'm only going 1 pi's amount of that. What's more is I cannot start at 0. I must start off 0. I must start at a max or a min. Okay? So this is where this can get challenging with these functions. After switching this, everything else falls into place. So this is what these 6 trig inverse functions and their graph look like when properly restricted. The next slide. This is what they should look like. This is what they should look like. This is the only way that they meet the criteria for being inverse functions. Questions here? Now, looking at these closely, you might notice some issues there with some of these. For example, when I look at the inverse function down here at the bottom left, for secant and for cosecant, those are not continuous everywhere. Those are not continuous everywhere, meaning that we cannot take a derivative after a certain point. We cannot do an integral at a certain point. We need to be careful of that. Tangent and cotangent both have asymptotes to them. We need to be careful with those as well. Questions here or concerns here about this one, about what we're looking at here? So, when you evaluate an inverse trig function, let's keep some things in mind. Keep some things in mind. Let's remind ourselves what's happening here. The reason why I'm trying to go a little slower through this rather than just here's the rules, let's do it, is because you guys have seemed to be intimidated by the trig functions all throughout this entire class. Anytime I put one of them up, you guys seem to hesitate a lot. So that's why I'm trying to ease our way into this a little bit more. Do a little bit more building before we get into the actual math, okay? So remember that an inverse trig function's job is to spit back an angle. Now, if we're going to do this, you have to remember that we cut down what angles we are allowing. We're only allowing for, let's go back to sine, negative pi over 2 through positive pi over 2. Anything outside of that window is not acceptable to us. So anything outside of that. So that's negative 90 to positive 90 if we're talking degrees. So something like 120 does not work for us. Okay? We need to be careful of this. You have to make sure that the angle that you are given falls within the specific domain. I will also remind you, of course, that most of your calculators don't have secant, cosecant, cotangent. It doesn't matter how nice or fancy they are. Most of them don't. My brand new one back there that I got on beta version from a brand new company has them, but you guys can't, and you guys will never be allowed to use those types of calculators. That thing can do calculus for you. It's the most elaborate and most advanced calculator I've ever seen. So, if you do need to use inverse sine, or excuse me, secant, cosecant, cotangent, do remember, of course, that you can use sine, cosine, and tangent to help. You guys remember how to do that. Let's say, okay, then prove it. Prove it. What is secant of, let's say secant of 2. What's secant of 2? What's secant of 2? Plug it in. Tell me what it is. Make sure you're in radians. Okay, so what are we punching in our calculators? I want to know. 1 over cosine of what? 2. Okay. So that's an equivalent form, right? 1 over cosine 2. So another one. Okay, I don't want to spend forever doing this. Look, you can also use this. You can also use inverse. I could also just do inverse cosine of 1/2. It might not spit out the exact same answers though, because of course you might need to find a coterminal counterpart here. For example, if you pick up your calculator and you type in inverse cosine of 1/2 of 0.5, you're going to get 1.04719, blah, blah, blah. If you do it the other way, as you guys said, 1 over cosine of 2, you're going to get negative 2.40, blah, 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 which is just the coterminal counterpart. Nonetheless, I don't really care how you plug it in the calculator. Just know how to plug it in the calculator, okay? At the end of the day, that's what I need. So, let's try it a little bit differently. Mr. Kaufman throws his keyboard on the ground and brings up the HTML code. Good work, Mr. K. Let's try to fix our slide. No, now I done broke everything. There we go. All right. So, without a calculator, spit these backwards. Using only your knowledge of the inner circle, on the next slide, can you spit these backwards? You tell me what value we're dealing with. This might seem arbitrary, but I'm telling you, it's a lot easier than relying on the calculator because you're not going to get very nice, neat numbers out of that calculator ever. But if you can switch these over back to their radian values, you're going to be a lot better off. Don't use that either. All right, guys and gals. We'll start going through. What's the first one? 5 or 6. When is sine? When is y? 1/2. It's at 5 or 6. Okay. What about the next one? When is cosine? When is x 0? 5 or 2. Very good. Okay. Next one. Tangent root 3 over 3. 5 or 6. What about secant -1? What does that mean? Come on, we just add it up here. What's secant? 1 over cosine. Okay, so when is cosine -1 then, right? When's that happen? At pi. Okay. I get inverse sine of 1. What's inverse sine short for? Guys, when is the y value 1? At pi over 2. Why was that one so hard? That's an easy one. It just throw you guys or what? Like,
I don't know, the way you asked it confused me.
did I say something weird?
I didn't know if you were asking for the answer for like another name for sine, inverse sine.
Oh, my bad. Well, then tell me.
So that's why I was just asking this.
Sometimes Mr. Coffin hasn't had enough coffee, as in the case of today. What about our last one? When is tangent -1? When we look for here? Tangent is 1 over what? Sine over cosine. So we need them to be the same for this to be a 1, right? So when is this going to happen? At -pi/4 or 7pi/4. There's another one. There's 2 answers here. What's the other one? At 3pi/4. Very good. So -pi/4 works. 7pi/4, 3pi/4. Now the reason why I take -pi/4 is because, as we're going to talk about with these limiting the domain, limiting the cycle here, so to say, right? This is where having those other options come into play, where 7pi/4 would not be maybe a necessarily good answer, but -pi/4 might be a good answer. You understand why that's important to know how we are restricting our function, how we're restricting that cycle. This isn't any different, gang, than when I taught it to you all the way back in pre-calc, depending on how long ago that was. When we did these exact same problems in pre-calc, I always limited you to a specific interval, whether that was 0 to 2 pi, which is what it was typically normally, or -pi to pi. I always limited your interval. We're doing the exact same thing here now. It's just that we're doing it a slightly different way than before. Okay? So, there you go. There's the inverse trig functions and their derivatives. So much fun. I know. The quick answer here to, can't I just write this as 1 over, I don't know, cosine, for example? No. No, you cannot. You cannot convert these back to the original 6 trig functions because we are limiting this so that these are functions in their own right. The original 6 trig functions don't have to have a limited domain or range. These ones do. For those of you that have your book with you, the For those of you that have your book with you, there's 2 pages I'd like to point out to you. Page 376 is where you will find this table specifically. Page 376 is where you will find this table specifically. Page 378 has, I think, a more important table, a more helpful table, which is the 24 basic trig derivatives or basic derivative rules I have given you to this point. That one is page 378. Up to and including these derivative rules. I think page 378 is something that I would absolutely sticky note. I would absolutely want to make sure that I know this. As we are talking about, and we talked about the AP exam earlier today, you need to understand that those 24 formulas there, you would have to know and have memorized by your AP exam. And their 24 counterparts for integrals. Are we ready to move on, to actually start applying some of these rules? Yes? Okay. So, the reason why I had you answer those questions before we do that, before we move along, the reason why I showed you those and made you do those, 6 or 8 inverse trig questions real quick, is because when I ask you to do this for homework or tomorrow for definite values, plug in this to your derivative, or tomorrow when we do integrals of this, plug this back into your integral, you actually can plug those values in and tell me what we're going to get back, whether it be pi over 6 or what have you coming back. Okay? Let's go ahead. Let's jump into my first problem here. So y equal to arc sine of 2x. Of course, arc sine is just a fancy way of saying sine inverse, right? We should be comfortable seeing both. Be comfortable seeing both. We're going to take the derivative of this. Take the derivative of it. So, what are we looking at here? We're going to have dy dx equal to what? Go ahead, Mark.
2 over the square root of 1 minus 2x squared.
2x quantity squared like this, right? Okay, so let's just make sure Parker's on the right track. He set the interior of his function equal to u. Yes? So arc sine u, 1 minus u squared in our root underneath, and times the derivative of u, which is just 2. Only thing that we might want to do here is a little simplification. Parker, and make this 4x quantity squared. Questions here? Trying to start us off with an easy one before we inevitably build to some of the more difficult ones. Let's move on to the next slide. What slide are we on by now? I've lost track.
10.
Slide 10. Slide 10. So let's give this one a try. Luke?
You're gonna get 3 over 1 plus 3x 20 squared.
3 over 1 plus
3x. 20 squared. Right.
just like this.
I think so, yeah.
Let's double check our rule. Now look at arctangent. I got derivative of what's inside, so 3, I like that, over 1 plus the inside squared, right? I think it looks good. The only thing I would do here, Luke, of course, is simplify. What are we going to get?
3 over 1 plus 9x squared.
Very good, very good. Questions here, issues here? Okay? Here's my next one. See if you can figure out my steps. My next one, here's my answer. What did I do? Who thinks they've got the right steps? Miss Grice. Let's give everybody else just another minute. See if they can get there. And then I'll have you help us out. You just helped us with a bunch of them here today. I'm about to start going back to the old math 2 rules of popcorn around the room if we don't get more people involved. But, okay. Stack your fractions. Yeah. All right, Allie. I'm tired of waiting. Let's go. What are we doing, Allie?
So u is equal to root x.
Okay. U can be equal to square root x, which makes du
1 over 2 root x.
1 over 2 root x. So, when you do our sign formula here, what are we looking at?
U prime over root 1 minus u squared.
Okay, so according to Allie, this should be 1 over 2 root x all over square root of 1 minus root x quantity squared, right? Or if we simplify down a little bit, 1 over 2 root x over square root 1 minus x. Are we all okay so far? Okay, let's double check where Allie's at. I like it so far. I'm going to combine these. I'm going to unstack my fraction. Okay, you guys remember how to multiply roots? The only criteria is that they have to have the same power, same degree of roots. Well, they're both square roots. So across the top, I got 1, multiply the things out front, 2, multiply the things inside, x, and distribute it through x minus x squared. Questions here about this one? Concerns here about this one? Okay, let's try this one out. Let's mix in some stuff from before. Let's mix in some stuff from last week. Okay, let's give it a shot. Brian, what are we going to do here, sir?
Set u equal to e to the power of 2x.
U to the 2x. What does that make u prime?
2e to the power of 2x.
2e to the 2x, right? E to the 2x doesn't, I mean, it doesn't really derive, right? It just spits back. And of course, the 2 comes from the chain rule for the exponent. Okay? So how does this help us here with our formula? Let's write this out. What's the formula here for our secant?
It is 2e to the power of 2x over the absolute value of 2, I mean, e to the 2x, and then the square root of e2x squared minus 1.
So this is what we're looking at here, right? It's our jumbled mess. So, Ryan, let's go ahead and start taking care of a few things. Now, the first thing I can tell you is you don't really need these absolute value bars because that is already a positive number. E is already a positive number, and it's 2 powers, so it's always going to be a positive number. So we don't really need the absolute value there.
And then you cancel out the e2x.
Absolutely. That gives me a 2 on the top. What can we do inside these roots here, sir?
You can bring in the square root.
I can multiply my exponents here, because that's how that's going to work, right? So this is going to become e to the 4x and minus 1. Let's check and see how Ryan did. Everything looks good according to my steps up there. Everything's on pace. Questions or concerns for this one? All right, then. Move on to the next one. This one might take a minute. Okay.
Check this out, what these right here, right? You just found out it really open here. How are you doing that?
Well, not a product. Mr. Kaufman copied down his own problem wrong. So. Let me see what you're doing. Well, but, other parts of the wrong track now. All right, let's get into it. Let's get into it here. How about Allie, pick somebody. Somebody I haven't heard from today. Heard from you a bunch. You give me somebody I haven't heard from.
Luke.
Luke.
I already went.
Luke's already gone. He did get involved today.
I got
Dawson. Dawson, where are we going to begin, bud?
So I guess you could just first like get separated and find the derivative of both of them.
Yeah. We'll treat this as a derivative, and then that as a derivative, we'll see what we can put together. I think that's the right game plan to take. Where would you like to begin with that? I see a product rule, and I see the inverse sign. Which one do you want to deal with first?
Just inverse sign.
Okay, so the inverse sign rule, that should just be u derivative over 1 minus u, right? So that's going to be 1, right? Over square root of 1 minus x squared, correct? Okay. Now for this second half here, this is going to be a product rule, correct? Okay. So what I would do here is first I would rewrite it as x and then 1 minus x squared to the 1/2, because you're right, there's going to be not only a product, but a chain in that product rule as well, right? So let's go ahead, let's do this. F's derivative is easy, that's 1, correct? G's derivative, a little bit more involved. What's G's derivative going to be? If you want, we can just write it out and simplify. You're hesitating. Let's write it out and let's do it ourselves. So we'll bring the 1/2 down, correct? We'll have the 1 minus x squared to the negative 1/2 now, right? Times the derivative of what's inside, which is negative 2x. Okay? Good so far? Yes, I mean, don't fib to me. Yeah? Okay, let's get these 2's out the way. Let's convert this to a fraction. This is going to be negative x on the top and square root 1 minus x squared on the bottom. Do you see why I want it as a fraction now? Because you see where it's going to get put together, right? Okay, so let's do our actual product rule here. Let's do our product rule on this thing. So that's going to be g times f derivative. Well, that's going to be easy because that's just g. So that's just plus 1 minus x squared to the 1/2. And then we're going to have plus f g derivative, which is going to be plus x times negative all over this nice fun looking fraction. Agreed? Why is it a negative? Because it's minus x squared. Good? All right, let's take a checkpoint. Let's see where we're at. Take a checkpoint, look and see where we're at. Okay, so what you got in red on the board is what I did over here in black. I simplified all that out. I plugged it in all on the board there. In green at the tail end is actually our middle part right here. And then, of course, what we have in blue is right here. Everybody good so far? Okay, so Dawson, believe it or not, most of the hard work is done. Now we just got to simplify what we can simplify, okay? Okay, so let's deal with this mess first, and let's put it in with this mess all at the same time, okay? Good with that?
Sure.
You see how they both have the same denominator, right? Okay, so we got 1 cohesive 1 minus x squared, and on the top we're going to have 1 minus x squared actually as well. Because the x times x is going to give us negative x squared, correct? And then we just combine them. Are we all okay so far with what I've done there? So that's these two dealt with. Okay, let's break down this mess. Plus square root 1 minus x squared. Are we all okay so far? Yes? No? Maybe. Okay, Dawson. Next thing I want to do is continue to put some more stuff together. Okay, so this is about where we're at right now. I can actually put all this together. So what I did on the board there is I unstacked that bottom. Let's put it all together, and I think it'll work better for you. Let's put it all together, okay? There's a couple of different ways we can approach this. Are you good, or are you starting to decipher that?
Sure.
Where are we at? Do you want to do it that way, or want to try to do it a little different way?
I can't even understand what's happening.
Okay, so what's happening up on the board, Dawson, is I just simply made this into 1 minus x squared to the 1/2, just like that. Okay? Good so far?
Yeah.
See what I've done to my denominator?
Uh-huh.
Okay, that's it. That's all I did. It's the only difference.
Yeah.
Okay, so we're here.
And then what just happened?
Okay, so to the right of this.
Yeah.
Okay? We're going to try to put all this together. Okay? So, Dawson, what I want to show you here is, you see how these are the same groups, yeah?
Yeah.
Okay, so this is the group 1 minus x squared to the first power, right? That's what I have there, over 1 minus x squared to the 1/2, right? What happens when you have common on top and bottom? What can you do with the exponents? Yeah, if I have something like x to the 5th over x to the 4th, I subtract them and get x, right? Or if I had x to the 3rd over x to the 1st, that would be x squared, right?
So that's supposed to be, is that a negative one right now?
Give me 1 second. We've done this before with 3/2 over 1/2, haven't we? It snuck its way into a couple of problems in the past, hasn't it? And this reduces down to be x over the 2 over 2, or x equals 1. Dawson, all I'm going to do here is I'm going to subtract these exponents. 1 minus 1/2 gives me another 1 minus x squared to the 1/2. Or square root. Square root. Those are the same, aren't they? I can add them together and make one cohesive root. There's my answer. The other way to do this is the way that I imagine some of you probably went instead, which is right here, where I asked Dawson what he wanted to do next, and I suggested we put them together. I just went about doing it a slightly different manner. Instead of creating common denominator top and bottom, we could have done, I went ahead and reduced the first one down to a singular term. I got rid of the fraction for the first one. Are we okay with this? You could have went with the common denominator route. You would still have to reduce at the end. You're still going to have to reduce at the end. Let's move on. Last one, I think. And if not, it's going to be because we're running out of time. But yeah, we got time for this one. It's only 11:30. Not even 11:30. 11:28. Dan Dawson. I only really threw you to the wolves by making you do that problem. Not the way I would approach it.
Now, Mr. President, if I were to distribute what? Or not distribute, sign multiplier. For what now?
Well, first thing I would do is just make them all at one cohesive fraction.
This one.
Second thing is I don't know where to get arc sine from.
Here, I'm in R10.
Dawson, who's doing this one, buddy? Throw somebody under the bus. Yeah, hit by a freight train before, so you pick somebody. Who's going? Michaela. Michaela, how did you approach this problem? Brought the 2 down. Did you chain rule? Did you use substitution? What you do?
No, I just put it in front.
Okay, so y equal 2. Did you keep arctangent or did you go to tan inverse? Which one did you use? What notation? Arctan. Okay, so 2 arctan of x. Okay, now what?
I did
So the answer to my question earlier was I did the chain rule, Mr. Kaufman. I didn't use any use substitution. I just went to the chain rule. Okay, so the chain rule then. So a derivative of the interior, derivative of arctangent is?
1 over 1 plus x squared.
Very good. Okay. Okay, let's put it all together. 2 arctangent of x over 1 plus 1 dx squared. Correct? And we're done. Sir?
Can you use substitution for that with the R10?
Sure I can. Sure I can. Set u equal to arctan. That makes du, or u prime, the 1 over 1 plus x squared, right? And then to rewrite this as u sub, this would be u squared, which that makes dy dx, 2u times u prime, which is 2 arctan times 1 over 1 plus x squared. And you're back to blank. I mean, at this point, the u substitution is merely just an occasional thing for something like this problem. And if you don't need to do that, then then don't. I mean, it's up to you. I'm not going to nitpick as long as you have the right work and the right answers. Questions here about this one? Okay, there's your homework assignment. There's your homework assignment. Let's go ahead. Let's get started with that. And just to reiterate again, the next time you guys come in here tomorrow, things are going to look pretty different in here. To answer this question that came up in Math 2, which I don't think you guys are silly enough to ask, but I will go ahead and address it. Obviously, you cannot stay in the same seats because none of the seats are staying where they're at. The whole classroom layout has to change as I'm bringing in 10 desks into my classroom. So no, obviously you can't really have the same seat because your seats aren't going to look like this anymore. We will have to come up with a new seating chart. We will do this after Easter break when everybody is here. In the meantime, just sit wherever.